Welcome back to Mindcast, the podcast where we dive deep into the fascinating world of artificial intelligence and cognitive science. I'm your host, Will, and today we're exploring one of the most groundbreaking developments in AI, something that might sound like science fiction, but is happening right now in labs around the world. We're talking about machines that dream.
Now, when I say machines that dream, I'm not talking about robots having nightmares about electric sheep. I'm talking about AI systems that have developed the ability to run internal simulations, to imagine scenarios, predict outcomes, and essentially dream up different possibilities before taking action. It's a capability that's revolutionizing everything from robotics to autonomous vehicles, and it turns out it might be the key to unlocking true artificial general intelligence.
What makes this even more fascinating is that this isn't just some random technological breakthrough. It's a case of convergent evolution. AI researchers have independently arrived at the same solution that nature figured out millions of years ago in human brains. We simulate, we imagine, we dream up scenarios in our minds before we act. And now, AI is learning to do the same thing.
So let's start with the human blueprint. How do our brains actually work when we're planning, predicting, or just thinking through a problem? Well, according to something called the simulation theory of cognition, proposed by researchers like German Hesslo, thinking isn't really about consulting some internal rulebook. Instead, it's about running simulations, what Hesslo calls simulated interaction with the environment.
This theory breaks down into three fascinating components. First, we have simulated behavior. Your brain can actually activate the same motor structures you'd use for a real action, but then suppress the final execution. Think about mentally rehearsing a piano piece or visualizing your golf swing. Your brain is literally going through the motions just without moving your body.
Second, we have simulated perception. Your brain can activate your sensory cortex without any external input. When you imagine the sound of your favorite song or visualize a sunset, you're literally using the same neural pathways as if you were actually hearing or seeing those things. It's remarkable when you think about it.
And third, the most crucial part, anticipation. Your simulated actions can trigger simulated perceptions of their likely consequences. So when you mentally rehearse sprinting in a race, you can also imagine feeling exhausted afterward. This predictive loop is what allows us to plan, to think ahead, to weigh our options before we act.
Now, here's where it gets really interesting from a neuroscience perspective. This isn't just a metaphor, it's physically measurable. Studies using functional MRI have shown that when you engage in motor imagery, mentally rehearsing a movement, you activate the exact same brain regions as when you actually perform that movement. The only difference is a downstream inhibitory mechanism that prevents your muscles from actually moving.
And here's the kicker. This mental rehearsal actually improves your physical performance. Athletes who spend time visualizing their performance alongside physical practice show measurably better results than those who only practice physically. There's a functional equivalence between imagined and real actions, which gives us a biological precedent for why internal simulation might be so powerful.
So that's the human blueprint. Now let's talk about AI's artificial counterpart, what researchers call Generative World Models. These are essentially AI systems that have learned to create internal simulated versions of their environment. They can imagine or dream by running generative simulations of potential futures, and then use those simulations to make better decisions.
Now, it's crucial to distinguish this from something called a digital twin. A digital twin is an external, high-fidelity replica of a known system. Think of a detailed computer model of a factory or a bridge that engineers use for monitoring and testing. But a world model is completely different. It's an internal, learned, abstract representation from the AI agent's own perspective. It's not trying to be photorealistic, it's trying to be useful. Think of it this way. When you imagine walking through your house in the dark, you're not creating a pixel-perfect visual representation.
You're creating a compressed, task-relevant model that captures the important stuff, where the furniture is, where the doors open, where the stairs are. That's what a world model does. It learns to compress the world, discarding irrelevant details to focus on the dynamics that actually matter for the task at hand.
The turning point for this field was a 2018 paper called Simply World Models by David Ha and Jürgen Schmidhuber. This work provided the first concrete framework that explicitly connected cognitive science concepts to functional AI agents. They split their agent into three parts: V for vision, which compressed high-dimensional observations into abstract representations; M for memory, which learned the dynamics of how the world changes over time; and C for controller, which made decisions based on information from the other two components. Here's what blew everyone's minds. The controller could be trained entirely inside the hallucinated dream generated by the memory component. The agent learned to solve tasks like car racing by imagining millions of scenarios in this compressed, abstract dream world. And this learned policies successfully transferred to the real pixel-based environment. It was proof of concept that learning by dreaming could actually work.
Now, fast forward to 2024 and 2025, and we're seeing some absolutely incredible developments in this space. Let me walk you through some of the most exciting examples. First, there's the Dreamer series, which evolved from that original 2018 work. The latest version, Dreaming version 2, solved a key problem. Instead of wasting computational power trying to reconstruct every pixel perfectly, it uses something called contrastive learning. The model dreams up a future scenario and is trained simply to distinguish the correct future from random alternatives. This approach proved over 30% more effective because it focuses on semantically meaningful dynamics rather than perfect visual reproduction.
Then there's Meta's V-JEPA 2, which represents a major step toward general-purpose world models. This system learns in two phases that mirror biological development. First, it's born by watching over 1 million hours of unlabeled internet video, learning an action-free intuitive model of physics, things like objects fall when dropped and liquids pour and fill containers. Then, in a second phase, it's fine-tuned on just 62 hours of robot interaction data.
The result? Zero-shot robot planning. Because the model already has a rich, simulatable understanding of the world, you can give it a goal, like an image of a grass object, and it can plan how to achieve that goal in a completely new environment without any additional training. It uses its internal predictor to imagine the consequences of different actions and selects the path most likely to succeed.
Google's Genie takes this even further. It's a foundation world model that can generate entire interactive playable environments from a single prompt. It's trained on massive amounts of unlabeled video, think 2D platformer games, but it's never explicitly told what actions are being taken. Instead, it learns to infer the latent actions that must have occurred between consecutive video frames. Then, during use, a human can provide actions, and the model generates new frames accordingly. It's like the model has learned a controllable understanding of causality from raw video.
And then there's SimLingo, which tackles a fascinating problem in autonomous driving. Imagine an AI that's learned to always slow down for pedestrians. If a human says, "Proceed," the person is waving us on. The model might ignore the language because its visual motor link is so strong. SimLingo solves this with something called action dreaming. The model is shown a single scene and then fed multiple conflicting language instructions. It has to imagine and generate the correct driving trajectory for each instruction, forcing it to align its linguistic and physical understanding.
So why does all this matter? Why is internal simulation such a game changer for AI? There are three fundamental benefits that make this capability transformative. First is accelerated learning and sample efficiency. Traditional reinforcement learning is incredibly sample inefficient. It learns by trial and error and requires millions of real-world interactions. But with world models, an agent can learn a simulator from limited real data and then train its policy entirely inside its own dreams. This is orders of magnitude more efficient and allows agents to acquire robust behaviors from a tiny fraction of real-world experience. Second is the critical sim-to-real bridge. Models trained with world models transfer better from digital environments to physical ones because they're not relying on human-designed simulations that might have incorrect physics. Instead, they learn their own abstract model of visual dynamics that more accurately represents their perception of reality. This is foundational for embodied AI, robotics, and autonomous vehicles. And third is foresight, planning, and counterfactual reasoning. World models allow AI to move from reactive behavior, if I see X, do Y, to predictive intelligence. If I do Y, I will see Z. Like Dr. Strange exploring millions of possible outcomes, a world model-equipped agent can simulate what-if scenarios before acting. This is the crux of reasoning, and it's vital for safety, allowing autonomous agents to rehearse hazardous scenarios or medical AI to simulate procedural outcomes without real-world risk.
Now, this brings us to one of the most heated debates in AI today, the path to artificial general intelligence. A major contingent of researchers, championed by figures like Meta's chief AI scientist Yann LeCun, argues that large language models, while impressive, are fundamentally limited. The LeCun doctrine posits that systems trained only on text are missing a crucial component: genuine understanding of the physical world.
LeCun and other deep learning luminaries like Demis Hassabis and Yoshua Bengio assert that world models are the essential path to AGI. They provide the physical intuition and causal understanding that text alone can never deliver. A 2024 MIT study provided empirical support for this. Researchers tested a top-performing language model on driving directions in New York City. The model gave near-perfect turn-by-turn directions, but when they analyzed its internal representations, they found it hadn't formed a coherent map of the city. Instead, it had generated an imaginary New York filled with non-existent streets. The model was generating accurate directions based on an inaccurate internal representation. And when researchers closed just 1% of the real streets, simulating construction or accidents, the model's performance plummeted. It had learned a bag of heuristics, not a simulatable, coherent model of the world. A true world model-based agent would have understood the map and simply planned a new route.
But, and this is important, internal simulation also presents significant challenges. The biggest risk is that the internal dream can become decoupled from external reality. AI hallucination is a perfect example. A generative video model creating a train with extra non-existent chimneys might be harmless, but a world model for an autonomous vehicle hallucinating a clear road when there's actually an obstacle is a major existential risk. There's also the problem of model collapse. If an agent trains too much on its own dream data, which contains its own biases and errors, those errors compound. The simulation drifts and diverges from the original data distribution, becoming a feedback loop where the model's performance on real-world data can plummet unexpectedly.
A crucial insight from 2025 research is that many world model projects are actually focusing on the wrong thing. The critique is that trying to achieve pixel-perfect simulation is computationally expensive, misses the point, and leads to failures in complex reasoning. A world model's true purpose should be to serve as a sandbox for reasoning. It should predict task-relevant semantic information, not raw pixels. The critical question isn't, what will this look like, but did the arm get closer to the object, or did the red cube tip over?
The proposed solution to building a reasoning sandbox that doesn't diverge from reality is hierarchical abstraction. The cutting-edge approach is something called the Generative Latent Prediction Framework, or GLP. This is a hybrid architecture that fuses language models with world models. At the high level, you have an enhanced language model backbone handling discrete, long-horizon planning. The conceptual level, like, I need to pick up the red cube. At the low level, you have a diffusion-based predictor handling continuous perceptual dynamics, the physics of how the arm actually moves and the cube tips.
This hybrid architecture grounds abstract symbolic reasoning in continuous perceptual simulation. It represents the most advanced proposed solution to the dreaming AI's grounding problem: how to keep artificial dreams tethered to reality.
So, where does all this leave us? I think we're witnessing a fundamental shift in how we think about intelligence itself. Internal generative simulation isn't just a cool feature or an add-on. It's emerging as a fundamental tool for any intelligent system that needs to operate under uncertainty. The parallel development of this capability in both biological and artificial intelligence suggests we're looking at convergent evolution, independent solutions to the same core problem.
The parallels to human cognition are profound and functional. Human dreaming serves to consolidate memory, regulate emotion, and run creative problem-solving simulations. AI world models serve the exact same functions: policy consolidation, counterfactual exploration, and generalization beyond training data. We're literally building artificial minds that dream, and those dreams are making them smarter.
The path to AGI is now inextricably linked to developing robust world models. The challenge isn't getting AI to dream anymore. Models like Genie and V-JEPA 2 can already do this with astonishing capability. The real challenge is ensuring that AI's internal subjective dreams remain coupled to objective, shared reality. We need to teach AI not just how to dream, but how and when to wake up. This is one of those moments in AI research where science fiction is becoming science fact. We're building machines that can imagine, plan, and dream up possibilities before they act. And just like human dreaming, these artificial dreams are making our AI systems more creative, more efficient, and more intelligent.
That's all for today's episode of Mindcast. I hope this deep dive into the world of dreaming machines has given you a new perspective on where AI is heading. The future of artificial intelligence isn't just about bigger data sets or more computational power. It's about building systems that can simulate, imagine, and dream their way to better solutions.
Next time, we'll be exploring another fascinating frontier: how AI is learning to understand and generate human emotions. Can machines truly empathize, or are they just getting better at mimicking empathy? It's a question that goes to the heart of what it means to be intelligent, and the answers might surprise you. Until then, keep questioning, keep learning, and keep dreaming. I'm Will, and this has been Mindcast.